we have defined the basic topology on our metric spaces, let us start moving towards the analysis on the metric spaces, or generally Rn, that we are going to be dealing with. Okay, and to do so, we start by first defining what are sequences and series is. Okay, so definition: a sequence Pn in a metric space is said to converge. A sequence, following the notation of the book, Pn in a metric space X in X. X is always going to be a metric space. We are not dealing with anything else. So X metric space is said to converge, is said said to converge if there is some integer, if there is a point P, if there exists P in X such that for every epsilon greater than 0 there exists an n greater than 0, well, n in naturals, such that n greater than or equal to n implies the distance between Pn and P is strictly smaller than epsilon. Okay? if P if Pn converges to P, we write limit n goes to infinity, Pn is equal to P. Okay? We say Pn diverges if it does not converge. We say Pn diverges if Pn does not converge. Oh, okay. So some people make a distinction of diverging to infinity and just diverging, or converging to infinity and just diverging. But we are going to follow the notation of the book, which says even if it's going to infinity, we are going to say it's divergent. Okay. Note: convergence depends on the metric space. Convergence depends on X. A set might not converge in rationals while it converges in reals. Um, for example, 1 over n converges in R1, but not in R greater than 0. Okay, so oftentimes in case of ambiguity, it is important to specify which space are we talking about. We say convergent in X rather than just convergent. Okay. The set of all points, the set of all points Pn n is equal to 1, 2, dot, 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 is said to be the range of Pn. Is the range of Pn, and it might be a finite or infinite set. Might be finite or infinite set, and the sequence is said to be bounded. Pn is bounded, is said to be bounded, said to be bounded if the range is bounded. If the range is bounded. So let's look at some examples. First, as n is equal to 1 over n, then limit n goes to infinity, Sn is equal to 0. Range is infinite, range infinite, but the sequence is bounded. Sequence bounded. Okay? The other way around, if I take Sn is just equal to n, then this diverges, then Sn diverges. The range is again infinite and unbounded. Range infinite, sequence unbounded. If the range is finite, then your sequence is always going to be bounded. Okay? The other way is not true. For example, in 1, we had that my sequence was bounded, but the range was infinite. Here's an example where the range is finite, I to the n. Then Sn is still divergent, right? However, the range is finite and sequence is bounded. Okay, so here are some examples. Okay, and now let us look at some of the major theorems related to convergent sequences. Theorem 3.2. Let Pn be a sequence in a metric space. Let Pn be a sequence in a metric space. X. Then first, Pn converges to P, converges to P in X if and only if every neighborhood of P contains all but finitely many points of Pn. Neighborhood of P contains Pn for all but finitely many n. Okay. Second, if P and P prime are in X, P comma P prime belong to X, and a sequence converges to both P and P prime, then they have to be equal. And if Pn converges to P and to P prime, then P is equal to P prime. Third, if Pn converges, then Pn is bounded. Converges, then Pn is bounded. Example 3 here was an example which shows that even if you're bounded, you need not converge. Okay, so the converse of C is not true. And D, if there is a subset E of X and P is a limit point of E, and P is limit point of E, then there's a sequence, then there is a sequence Pn in E such that P is equal to limit n goes to infinity Pn. If you have forgotten what it means by P being a limit point of E, let me reiterate the definition for you. P is a limit point of E if every neighborhood of P contains some point of E which is different from P. Okay, so that was the definition of a limit point. Now let us start looking at the proof. Most of these proofs are really easy, as this is the first theorem. So A, we are showing if and only if. So let's first show one direction. Suppose P converges to, suppose Pn converges to P. Okay, so this is another notation. Or Pn converges to P. Okay, this is another notation for writing Pn converges to P, which is slightly lazier than the other notations. Okay, suppose Pn converges to P. Let V be a neighborhood of P. V B N B H D of P. Okay. If Pn converges to P, then for some epsilon greater than 0, the condition well, I don't even need to say the condition. For some epsilon greater than 0, d of q comma p smaller than epsilon with q belongs to x implies that q must belong to E, right? So if I take V to be a ball of neighborhood of radius epsilon, not E, V. Okay, I can, if V has radius, right? V has radius epsilon, right? If I take radius of V to be epsilon, then there is some an epsilon such that distance of q comma p smaller than epsilon implies q belongs to V. Well, what does that mean? Therefore, corresponding to this epsilon, there exists an n in n such that n greater than or equal to n implies df comma p smaller than epsilon. Well, therefore, n greater than or equal to n implies pn belongs to v. Right? So everything after capital N has to belong to this ball of radius v. To show the other way, the idea is going to be the same. Suppose every neighborhood of P contains all but finitely many P. Suppose every NB of P contains all but finitely many of the Pn. Okay. Then what do? Fix epsilon greater than 0. Fix epsilon greater than 0. Let V be the V is equal to ball of radius epsilon centered at P in X. Okay. Then what do we have? Then there exists an n in n in naturals such that Pn belongs to V if n greater than or equal to n by assumption, right? Because there are only finitely many of them which are not in the ball. Take the biggest number that is not in the ball. Everything after that is going to be in the ball. Therefore, d of Pn comma P is smaller than epsilon for every n greater than or equal to n, and therefore Pn converges to P. Okay, relatively straightforward both ways. Second, if P and P prime are not equal, okay, then they are going to have some distance. So let epsilon greater than 0. Take some epsilon greater than 0. There exists, take epsilon greater than 0. Take, then there exists n1 comma n2 such that n greater than or equal to n1 implies distance between Pn and P is smaller than epsilon over 2. N greater than or equal to n2 implies distance Pn comma P prime smaller than epsilon over 2. Okay. Then take n which is greater than or equal to max of n1 and n2. What do we get? We get the distance between P and P prime must be smaller than the distance of P n and P plus distance of Pn and P prime by triangle inequality, which is strictly smaller than epsilon. And since this is true for every epsilon greater than 0, it has to be as this is true for every epsilon greater than 0, this implies distance of p comma p prime is equal to 0, which means that therefore p is equal to p prime as required. Okay. Part C. What does part C say? Scroll back up. Part C says if Pn converges, then Pn is bounded. Okay. Suppose Pn converges to P. Suppose Pn converges to P. Okay. Then there exists n belonging to n such that n greater than or equal strictly greater than n implies the distance of Pn and P is strictly smaller than 1. So if I take epsilon is equal to 1, there is some n such that this works out. Well, put r is equal to a maximum of 1 comma distance of P1 comma P, distance of P2 comma P, dot 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 Pn comma P, distance of Pn comma P, then I have that distance of Pn comma P is smaller than or equal to r for every n. Okay, and hence that means Pn is bounded. Therefore, is bounded. Okay, and then the last part, we want to show if E is a subset of X and P is a limit point of E, which is to say for every neighborhood of P, you have at least one point in E, then you can find some sequence in E which converges. Okay. The idea is going to be really simple. You're going to take one point in each neighborhood. For each n belonging to n, there exists a point Pn belonging to E such that distance Pn comma P is smaller than 1 over n. Right? Now, given epsilon greater than 0, choose n such that n epsilon is greater than 1. Then n greater than capital N implies distance of Pn comma P is strictly smaller than 1. Okay? Smaller than epsilon. Sorry, not 1. Smaller than epsilon. Because if n epsilon is greater than 1, then epsilon is greater than 1 over capital N. And if small n is greater than capital N, then 1 over capital N is smaller than 1 over small n. Sorry, 1 over capital N is bigger than 1 over small n. So distance Pn comma P, which is smaller than 1 over small n, is smaller than epsilon. Therefore, Pn converges to P as required. Okay, and that completes the proof for all 4 cases, all 4 parts. Okay, we don't have to just restrict ourselves to R, we can look at sequences in complex numbers, and a lot of nice properties of sequences in complex numbers are a lot of nice properties of sequences in R are similar to those in complex numbers. So we'll just prove them in more generality for complex numbers, and then they are going to be true even for real numbers because they're just a subset. Okay? Theorem 3.3. Suppose Sn and Tn are sequences of complex numbers. Suppose Sn, Tn are complex sequences. And the limit of Sn is equal to S, and Sn converges to S, Tn converges to T. Okay? Then, first, limit of n goes to infinity, Sn plus Tn is equal to S plus T. Second, limit n goes to infinity, C times Sn is equal to C times S, and limit n goes to infinity, C plus Sn is equal to C plus S for every C belonging to complex numbers. Even if it's 0, this holds pretty well. If it's negative, positive, nothing, well, negative and positive is not exactly a concept in C, but it holds for every complex number. Limit n goes to infinity of Sn times Tn does exist, and it is actually equal to St, as you would hope. Okay? And last but not the least, limit n goes to infinity of 1 over Sn is equal to 1 over S, as long as, so provided Sn is not equal to 0 for every n, and S is not equal to 0. Okay? Proof. The last condition, that Sn not equal to 0, just as saying that this sequence should make sense. If even one of these terms is 0, then 1 over Sn does not make sense. So you need it to be non-zero for every single term. Okay. Proof. Again, this is, most of it is going to be relatively simple. Given epsilon 0, given epsilon greater than 0, there exists n1, n2 belonging to n, such that n greater than or equal to n1 implies Sn minus S is smaller than epsilon over 2. N greater than or equal to n2 implies Sn minus S smaller than epsilon over 2. And therefore, as expected, as before, taking n greater than or equal to n is equal to max of n1 comma n2, we get that Sn plus Tn minus S plus T is smaller than or equal to Sn minus S plus Tn minus T, which is strictly smaller than epsilon. Okay. This proves A. B is trivial. Trivial left as exercise. Okay. C. This requires a slight bit more amount of effort. It's not really hard though, still. Note that. Okay, not note that. Use Sn minus Sntn minus St is equal to Sn minus S times Tn minus T plus the cross terms that are unfortunately going to pop up, which are S times Tn minus T plus T times Sn minus S. Okay. Well, how do we use this? Given epsilon greater than 0, once again, there exists n1 comma n2 belonging to naturals, such that, well, this time we don't want it to be less than just epsilon over 2 or something. We are taking product. So n greater than or equal to n1 implies distance s minus s Sn minus S is smaller than root epsilon. N greater than or equal to N2 implies Tn minus T is smaller than root epsilon. Okay. Then N greater than or equal to N is equal to max of N1 comma N2 implies well, S minus Sn times T minus Tn is smaller than epsilon. Okay. S minus Sn times T minus Tn is smaller than epsilon. S times Tn minus T is smaller than S root epsilon plus T root epsilon. Okay. Therefore, first of all, this implies that limit n goes to infinity S minus Sn Tn minus T well, whatever is equal to 0. Sn minus S Tn minus T. Sn minus S Tn minus T is equal to 0. Now, if we apply A and B, applying A and B to star, let me call this star. I've shown that this part is going to 0, right? Parts A and B are saying, oh, if this limit is going to 0, then constant times this is going to 0. If this limit is going to 0, constant times that is going to 0. All of that goes to 0. So the difference goes to 0. So limit n goes to infinity, Sntn minus St is equal to 0. And therefore, that is exactly what we wanted, because that tells me that limit Sntn is equal to St. Okay. For D, choose m such that Sn minus s smaller than 1/2 s if n greater than or equal to m. Okay. Well, if this is true, then rearranging by triangle inequality, therefore, Sn is greater than 1/2 absolute value of s for every n greater than or equal to m. Okay. Now, given epsilon greater than 0, there exists an integer n in n such that um, uh, n greater than or equal to n implies Sn minus s is smaller than 1/2 absolute value of s squared epsilon. Since all of these are constants on the right hand side, I can choose my epsilon and n such that it works out. Given any epsilon, I can choose n such that it works out. Hence, for n greater than or equal to n, we have that 1 over s, 1 over Sn minus 1 over s, which is equal to Sn minus s over Sn times s, is smaller than, well, the top is smaller than 1/2 s squared epsilon. So 1/2 s squared epsilon times Sn times s, which is, I have bound my Sn by 1/2 s, so times 2 absolute value of s times 1 over s, which is strictly smaller than epsilon. Well, this is actually just equal to epsilon. Is equal to epsilon, right? And hence, I have shown that there exists n for which this difference is smaller than epsilon, and hence the sequence converges. Okay. Theorem. For multidimensional sequences, so theorem 3.4, part A. Suppose we are not in R1 or complex numbers. Suppose we are in n dimensions. Suppose xn belongs to Rk for every n to n, and xn is equal to alpha 1 n. Why this horrible notation? Alpha kn. Then we say that xn converges to converges to alpha or x, whatever. Then xn converges to xn converges to x, which is equal to alpha 1 dot 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 alpha n, if and only if limit of each of these subsequences is a very specific term, so I'm not going to call it subsequences. Limit of each of these other sequences, alpha jn, is actually alpha j for every j which is between 1 to n. So for every 1 smaller than or equal to j smaller than or equal to k. Okay, so more or less we are saying that if it's a multi-dimensional sequence, we say it's convergent if it converges in every single coordinate. If it's a uh, if it's a sequence in Rk and it converges to x, then it should converge in every single coordinate. Suppose xn and yn are sequences in x, xn, yn, sequences in Rk, and bn, beta n is a sequence of real numbers, is a sequence of real numbers with xn converging to x, yn converging to y, beta n converging to beta, then limit n goes to infinity, xn plus yn is equal to x plus y, limit n goes to infinity, xn times yn is equal to x times y, and limit n goes to infinity, beta n xn is just beta times x. Proof? I won't do every single proof. I'm going to leave part B to you because it basically follows from part A and the previous theorem. Once you have shown that it has to individually be true for every single coordinate, now you're just saying, oh, these things hold for coordinates, so you should check. So for part A, okay, if xn converges to x, then the inequality is then the inequality is alpha j comma n minus alpha j smaller than or equal to xn minus x will follow immediately from the definition of the norm. Follow from the definition of the norm. So if this is smaller than so if xn minus x is smaller than epsilon, if xn minus x is smaller than epsilon, then alpha j n minus alpha j is smaller than epsilon. So if xn converges to x, alpha jn converges to alpha j. Okay? So this is which way? If and only if. Yeah, so this is this way. For the other way, suppose each of these do converge. If for every alpha epsilon greater than 0, there exists n belonging to n such that so nj, let me just say, such that nj belonging to n naturals such that n greater than or equal to n implies alpha j comma n minus alpha j is smaller than epsilon over root k. Okay, 1 smaller than or equal to j, smaller than or equal to k. Therefore, n greater than or equal to n is equal to max of n j's implies that the norm of xn minus x, which is equal to just summation j is equal to 1 to k alpha jn minus alpha j squared all to the 1/2. Each of this is smaller than epsilon over root k, so square and sum is smaller than epsilon squared over k. There are k of them, so in total sum is smaller than epsilon. Therefore, xn converges to x. Okay. Part B follows from A and theorem 3.3. Okay. Fill in the details. Fill in the details. Fill in the details. Okay. Let me define. Let's do a couple theorems of subsequences and then stop. Subsequences. Definition. Given a sequence Pn, given Pn, consider a subsequence. Consider a sequence nk such that n1 smaller than n2 dot 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 smaller than goes on. Okay. This notation is wrong. N1 smaller than n2 smaller than dot dot dot. Okay, there we go. That's the correct notation. Then the sequence Pnk is called a subsequence of Pn. Is called a subsequence of Pn. Okay. If the subsequence converges, if Pn Pnk converges, its limit is called sequential limit of Pn. Its limit is called a sequential limit. Limit of Pn. Okay. Note, it is clear that if Pn converges to P, clearly if Pn converges to P, then every subsequence converges to P. Then every subsequence converges to P. Prove it by yourself. Int. So proof as homework. Proof as homework. int same n works. Okay. What is not true is that if Pn if a subsequence converges, the sequence has to converge. However, even if a subsequence converges, Pn need not converge. And this is really easy to see. Example, let Pn is equal to -1 to the power n. Then Pn diverges, but P2n converges to 1 and P2n plus 1 converges to -1. Okay. Now the question of whether if every single subsequence converges to one point, then what happens is a much harder question that we'll not be dealing with right now. We'll talk about it later. Okay. The thing is, if every single subsequence converges to the same number, Pn itself is a subsequence of Pn, and that converges to the same number. So it trivially converges. Okay? So I don't think that's a meaningful statement, actually. Yeah. If every single subsequence converges to P, then Pn does converge to P because Pn is trivially a subsequence of Pn. Theorem 3.6. A. If Pn is a sequence in a compact metric space, if Pn is a sequence in a compact metric space, which will denote X, matrix space X, then some subsequence of Pn, then some subsequence of Pn converges to a point in X. Converges to a point in X. So it is not necessary that the sequence in that case has to converge, but there is a subsequence which converges. And every bounded sequence in RK has a convergent subsequence. Okay. Proof. B is again going to trivially follow from A. I will not write the proof of B. I will just write down the proof of A. Let E be the range of, let E is equal to range of Pn. Okay. If E is finite, then there is a P which takes which occurs infinitely. Then there exists a P belonging to E and a sequence Ni with N1 smaller than N2 smaller than dot dot dot, such that um, Pn1 is equal to Pn2 is equal to dot 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 Pni is equal to P. Right? Then the sequence obviously converges to P. Therefore, Pni converges to P. If it is not finite, if E is not finite, E is not finite, then we know that E has a limit point. Then E has a limit point P in X. Okay. How do we do this? Well, choose N1, choose Ni, such that distance of P and I, comma P is smaller than 1 over I. Okay. Choose distinct Ni. Choose distinct Ni such that this happens. I don't want to say this. Yeah, then P and I converges to P. Yeah. Okay. Small now. And Ni greater than Ni minus 1 such that this two happens. Okay. Then we have that D Pn comma P. Then Pni converges to P as required. Okay. Part B follows from A. Follows from A, and that every bounded subset of Rk is a subset of compact subset. Lies in a compact subset. Lies in a compact subset of Rk. Okay. Then let us do one last theorem and stop for the day. Theorem 3.7. The sequential limits of a sequence Pn in a metric space form a closed subset of X. The sequential limits of a sequence Pn in a metric space X form a closed subset. Okay, so this is a interesting theorem. You're looking at every subsequence, you're looking at its limit, including the finite subsequences, right? No one can, no one says that a subsequence cannot be finite. A sequence is allowed to be finite. Okay, just Pn is also a subsequence, and this theorem says if you look at all of them together, it is a finite set, not finite set, closed set. Okay, so let E star be the set of all sequential limits. Be the set of all sequential limits of Pn. Okay, and let Q be a limit point of E star. And let Q be a limit point of E star. Want to show Q belongs to E star, right? Because that's what it would mean to be closed. Your limit points should belong in there. So choose n1 so that Pn1 is not equal to Q. Okay. If there is no such n1, then E star has exactly 1 point and we are done. If no such n1 exists, then E star has only 1 point and then it is closed. Okay, so suppose such an n1 exists, then put delta is equal to distance of Q and Pn minus Pn1. Q comma Pn1. Okay. We are going to choose n1 to ni minus 1 in some way, and we are going to choose them iteratively. So suppose n1 to ni minus 1 are chosen in some specific method. I'm just being lazy. Since Q is a limit point, there is some since Q is a limit point, since Q is a limit point of E star, there is some x in E star. There exists x belonging to E star such that distance of x comma q is smaller than 2 to the minus I delta. Okay. Therefore, there exists some ni such that P of ni ni greater than ni greater than ni minus 1 such that distance of Pni and x is smaller than 2 to the minus I delta, right? Therefore, distance of p to the distance of q and p to the p and I is smaller than 2 to the I minus I plus 2 to the minus I, which is 2 to the 1 minus I delta. Okay, for now you can find such an I for every delta. For every I is equal to 1, 2, dot, 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 dot. So this is how you're choosing. Once you have chosen n1, you choose n2 such that this thing holds. Then you choose n3 such that this thing holds. N4. Then Pni converges to Q. Converges to Q. Therefore, Q belongs to E star. And hence, E star is closed. Okay. We'll stop here. Next part is going to include subsequences. Cauchy sequences, which we'll do next time.